The following is a full video from interviewpen.com. If you want some of the best explanations to challenging data structure and algorithms and system design content, visit our site. Get access to a lot more content. We publish 2 to 4 videos a week in system design and data structure and algorithms, and we're online 24/7 to answer any questions you may have. We're really building something great. Enjoy the video. So we're going to look at a problem called Stone Game here. And we have 2 actors. We're going to have an actor Alice and an actor Bob. And we're going to label Alice A and Bob B. And so it's best if I just explain the game with like a linear sequence here rather than just giving you the array and the output. We're going to output true if Alice wins the game. We're going to output false if Bob wins the game. And so essentially we're given an array here. And each of these indices, each of these positions, indicates a number of stones. We can also think of it as points. And each of these is a pile. So this is a pile of stones, and you can capture any given kind of pile within a certain kind of rules we are about to create. And so Alice is going to start the game. And the objective of the game is to collect as many stones as possible. And so you can pick up a pile on the left side or the right side of kind of the amount of kind of stones here. So each of these is a pile. You can only pick the pile on the left or the right. If you pick the pile on the right, that pile is going to disappear. You're going to accept that as your score. So in this example, Alice is going to take this 9 here. She chose between the 3 and the 9. And then Alice is going to take the 9. And then we're going to be left with these stones, and then it's Bob's turn. And then once it's Bob's turn, he can choose between the left or the right end. And then he, in this case, will choose the right end and then reap that as his score. So now it's 9-5. And so you take the pile of stones as your score. And then Alice can choose between the 3 and the 1 here. Alice is going to choose this 3, and then her score is going to go, from this 9 to this 12 plus 3. And then these are the stones that will be left, the piles that will be left. Now, Bob can choose either of these. It doesn't really matter. The game's kind of going to reduce to kind of the same thing. So Bob chooses the right, and then it becomes 12-6, so plus 1 there. And then Alice is left with this 1 and 4. And again, if Bob chose this, we would have had the 1 and 4. Alice is going to choose the 4, which is the better answer, at least in this kind of base case here. And then Alice is going to go up by 4. And then we're going to have Bob with a single item left. Bob chooses it, and Bob ends up losing. He has 7, Alice has 16, and we output true because Alice won the game. And so Alice starts. We're going to have these kind of piles of stones. You can choose from the left or the right side. There's an even number of piles. So Alice does not get an advantage, kind of a head start advantage by going first. If there was an odd number of piles, Alice could take this, Bob takes this, and then Alice takes this. And then she gets 2 piles, Bob gets 1. No, it's going to be even number of piles. So everyone's going to capture n over 2 piles with respect to kind of the array length, if we call the array length n. And there's going to be an odd number of stones. So we cannot tie. We can't have Alice have 10 and Bob have 10. It's going to have to be 11 versus 10 here or something like that. It's going to have to add up to an odd amount because we cannot tie. And so how are we going to go about this? Now, I want to give kind of my initial thoughts, as I always give my initial thoughts. I immediately see an opportunity to kind of simulate the problem. If you're given a problem description this literal, and there's decisions, there's many decision junctions, here's the first decision junction. And we're going to see this over and over as we go over this problem. We see a global array. I see a left side. I see a right side. Alice wants to make the decision that is globally optimal across all of the decision junctions. But wait, let's stop there. I hear globally optimal. I hear decision junctions. And as soon as I think of these things, globally optimal decision junctions, we're getting way ahead of ourselves. I think of dynamic programming. We're not there yet, but that's immediately what I see. But at first what I see is a recursive brute force. And so we can actually simulate the game itself, and we can do the moves, and we can see whether Alice wins. And so one thing I really like to do is draw out a recursion tree. Maybe you're not going to have the time to do this in an interview, but for teaching purposes, it's going to allow me to show you really what I kind of see in my head when we kind of have all of these decisions that can happen. So at this top level, Alice has two choices. Alice can take what's all the way to the left, or Alice can take what's all the way to the right. Now, let's imagine Alice takes this 4. What happens? We have this 1, 5, and 9 left over, and the state of the game changes. And now all of this is recursive state we would keep track of. We'd keep track of a left, we'd keep track of a right, we'd keep track of A's score, Alice's score, Bob's score, and that would, reduce the problem to this. And then the question is, Bob, are you going to choose the 1 or the 9? Bob can choose the 1 and go this way, or he can choose the 9 and go this way. If Bob chooses the 1, he's going to take 1 in score. If he chooses this 9, he's going to take 9 in score. And so the decision junctions go very deep here. And so I just kept this to an n equals 4 example because, this is going to, give us like 2 to the 4 with respect to kind of the combinatorics here. So, this would be 16 or so kind of leafs, I would imagine. And so on. And it roughly works out to that. We have 8 leafs down here. Bob would make a final decision down here and so on. So again, I kind of just gave away the time complexity here. We have n decision junctions. We have a decision here where Alice needs to make a decision. There's going to be n decisions. Alice chooses one, Bob chooses one, Alice chooses one, Bob chooses one. At each point, they had 2 choices. They had 2 choices they could have made. And so, we're kind of pins to a depth of kind of n decisions. At each point, our branching factor is 2. If you go back to the section on time complexities, recursive time complexities, and our video on the power sets, you can know that, this is basically big O2 to the n in time complexity. And in terms of space, we're going linear on the call stack. Again, we're getting ahead of ourselves in time complexities, but this is what's happening in the problem. There's a decision that can be made, and I see a lot of subproblems. And here's an interesting thing. This looks like the same subproblem. We have Bob making a choice, and the bounds are the same. This is an overlapping subproblem. Again, dynamic programming looks like a potential avenue for us. We have overlapping subproblems. And so when we're all the way down here, I want you to also consider the base case. So if we had a single item here, and at this point in time, it's going to be Bob's choice. So Bob is going to, choose this 9, at this very end point. Since, Alice chose a 4, Bob chose a 1, Alice chose the 9, and then, we're down to this 5, and Bob chooses it. If there's a single item, Bob's just going to take that single item, and that's a base case. So that's something that may factor in later. So anyway, we're trying to simulate a brute force here. We know it's going to be, exponential in time complexity, similar to the combinatorics of our power set problem. And we can see the state we need to simulate. So let's also kind of draw some observations from this overarching tree I wanted to kind of walk us through. There's going to be n decisions made with 2 ways per junction, right? And we saw those decisions. Choose from the left pile or the right pile. And these can be recursively simulated. Here's the thing. Some paths can never happen with optimal play. And here's something I should have explicitly said. Both players will play optimally. What does optimally mean? So let's imagine a player, before the game starts, both Alice and Bob get to look at this tree. And what's important to them is this down here. What is the final score? And so Alice can go to the left or Alice can go to the right. And I want you to notice, if Alice goes to the right and chooses this right guy, in every single potential outcome of the game, Alice is going to win. So what would Alice want to do? Alice would certainly want to go right rather than go left. And, maybe there's a higher score over here potentially, but, Alice is going to be chasing the highest score possible for herself. And so, in this subtree, that looks like it's 14. We have a 13 here. So going right looks good to Alice. And so what Alice is going to do is Alice is going to go right. And that's kind of the best way for her to kind of win. And so now that Alice goes right, these are kind of the possibilities. And then Bob has to say, do I want to choose this 4 or this 5? Now the score is 9-0. Do I want this 4 or this 5? Well, let's kind of look at how the game could unfold. Remember, Alice is going to play optimally. So although, Bob sees he could reap a 9 here, a 6 here, a 5 here, a 9 here, although Bob could go left, if Bob chooses this 4 and goes left, what's going to happen? Alice is going to take that 5. So Bob's going to want to jump and jump on that 5 because Alice is going to want to play optimally herself and to snatch that 5 away. So since Bob knows Alice is playing optimally, Bob is going to take that 5 and Bob is going to drive the recursion to the right. Remember, both players will play optimally. And this is key to the problem because they're going to preempt each other's behavior. And so Bob takes this 5. We're left with a 4 and a 1. What is Alice going to do? Alice is going to say, fine, I'll take this larger item and I'm going to drive the recursion to the left. And then we're left with this final result. And this is the likely outcome. If both are playing optimally, or this is the certain outcome given kind of how the problem is played out, if all our numbers are correct here, both players know the other is going to make the optimal global move. And so this is the score that would, end up happening with Alice going first because Alice plays optimally, Bob plays optimally given his decisions that remain. Alice plays optimally given the decisions that remain for her. Alice, we could have had a 14-5 score here, as you can see, but that would mean Bob would have made a suboptimal decision here by going left. He's not going to do that. He's going to make the best decision for himself and to kind of cut Alice off. And so, although this is worse for Alice, this is how the game would probably play out. In all of these situations, though, Alice is going to win in all situations. And so before the game starts, both players see this recursion tree. Let's imagine that's the case, and they're going to play accordingly. And so how do we simulate this recursion? So we're going to create a function called simulate, and exactly what we saw before is the parameters we're going to pass. Here's the top level call. The simulate function asks, given that this player has, a left and right boundary, they're looking at a left and right boundary. We pass in the piles, the Alice score, Bob score, and Alice going first. Given all of these parameters, return kind of the result of the game. Does Alice win or does, Bob win? And so, the initial inputs are the left is 0. The right is the length minus 1, meaning we consider the whole array. So this is the left, this is the right. Once we do that, well, we're also going to want Alice's score to be 0, Bob's score to be 0. And then we say, is this Alice? That's true at first, right? So we're going to start the simulation of the game. And so what is the base case? That's the first place. Let's forget about all of this stuff. What is the base case? If the left is greater than the right, meaning we're done looking at all the items, the game is over. If Alice's score is greater than Bob's score, that's a win for Alice. So, we're going to return true here. If Alice wins. What was the original question? The original question is, does Alice win? Does Alice win? That is the original question that we're kind of solving here with this kind of state we're passing in. And so we're just kind of working the problem definition into a brute force here, right? And so, and we saw the parameters are the left, the right. We pass on the piles of stones. We pass on their scores. And is it Alice? And so here's where the recursion goes first. Is Alice, if it's Alice, what is Alice going to do? Alice is going to have a left or a right decision Alice can make. If Alice wins by choosing the left item, or Alice wins by choosing the right item, the original question was, if I have this original array and Alice can choose the left or the right, can Alice win the game? And so that's exactly what we're simulating. And so what does the state transition look like? This is the next key thing in a recursive function. Well, if I choose the left item, then the left pointer closes in by 1. So, if we go back here, if I choose this item, left closes in by 1. If I choose the right item, right closes in by 1. And so if we go back, if we choose the left item, the left closes in by 1 to going to the right. The right stays the same. We just pass it on. The pile stays the same. It's a reference we pass on. Alice's score becomes Alice's score plus the value at that left in the piles. Bob's score stays the same, and Alice is false. Now it's Bob's turn in the next call. And then here, if Alice chooses all the way to the right, if Alice chooses all the way to the right, the pile over here, we're going to close the right pointer in by the left stays the same. The right pointer goes right minus 1. The pile stays the same. And then Alice's score changes by adding on the right. And that's how Alice's score changes. Bob's score stays the same. And then is Alice's false. And so this recursion is going to play itself. It's going to go all the way down and say, does Alice win choosing left? Does Alice win choosing right? For teaching purposes, I broke this into variables. In reality, I would just inline all of this down here. And maybe that allows us to have compiler optimizations to occur rather than kind of having everything in line to a variable. That's not necessary here. But for reading purposes, it makes it easier to read and teaching purposes. But so if Alice wins choosing left or right in the top call, everything pops up and then it's true at the top level. This is if it's Alice's turn. If it's Bob's turn, what will Bob do? Well, he's going to do something very similar. The only thing that changes here is that Bob's score is going to be what's incremented. Alice's score stays the same. We're still going to close in the left if we choose the left item. Right's going to stay the same. Pile stays the same. Alice's score stays the same. Bob increments his score by the left. Now it's Alice's turn. And then, same thing. Left stays the same. Right's going to close in by 1. If Bob chooses the right item, Bob's score gets incremented by the right item. Alice's score stays the same. And it's now Alice's turn. And so then he's going to return. Does Bob win choosing left, or does he win choosing right? These variables should be called Alice wins choosing left, Alice wins choosing right, because that's kind of the global questioning here. But yeah, these variable names are arbitrary, but really it should be, does Alice win if Bob chooses whatever? Bob does this left decision, Bob does this right decision. And so ultimately, this is going to simulate them taking turns. That's kind of the whole point of it. It's going to simulate them taking turns. And at the end of it, when we have no more items, we're going to see the final score. And then we're going to say, did Alice win over Bob? And so what was the time complexity? If we go back to this tree, again, we would be, n in depth. And then in terms of kind of branching factor, we'd have 2. So it's 2 to the n, very similar to the combinatorics of the same combinatorics essentially asymptotically as our problem on the power set. And then in terms of space, we're going to be using linear space on the call stack to kind of go n calls deep. Any other auxiliary space, none at the moment. Yeah, so it's going to be just the call stack dominating space. And so this is kind of a brute force. This is a brute force that simulates the problem exactly and tells us, if we play the game out, who wins following all decision junctions. Here's the issue. This assumes that each player is going to, go down decision trees that they would have never gone down. As I showed over here, Alice would not have gone left, but the recursion is going to simulate that. So, we're kind of doing all this work when we don't need to, because in reality, in the real game, Alice wouldn't do that. Alice would not do that. Alice would take to the right. And so we need to look closer at what the players actually are optimizing for and what are they going to do, and what's like the core decision they're making and how do we optimize for that. And as I was saying, we see subproblems here, and I want to take us back to what the core decision is. So I'm given a subarray, and we have a subarray from this left pointer to this right pointer, and then the question is, what is Alice's goal? Alice wants the maximum score. Alice wants to make the maximum score based on this subarray and based on being able to choose the left or right. And so we're crafting the states of the subproblem. This is very important for us to kind of craft, maybe a dynamic programming solution here. There's a left pointer and there's a right pointer, and then there's a subarray that we consider from the left pointer to the right pointer. The parameters to our subproblem we can clearly see is there's going to be a left pointer, a right pointer, and then we also might wonder, who's taking the turn? Is it Alice or Bob taking the turn? So in this case, the global subproblem, we say if an agent starts with the subarray from the left to the right, what's the best score they can get? How do they maximize their score at this move, given the global kind of like unfolding of the subproblem below? So Alice knows the best answer is 9 here. 9 is the best answer given how anything could possibly unfold below. And then, Bob sees that the best answer for him is 5 here, so he's going to snatch up the 5. Alice is going to see the 3 is the best answer here, snatches up the 3. Because if Alice snatches up the 1, she exposes this 4 for Bob to take. Okay, so Bob's just going to snatch up the 1, all he can do. And then Alice is going to snatch up the 4. Alice maximized through every single decision junction globally at the local decision. So we saw all of kind of the state of the subproblem. So let's kind of break this down into a recurrence that we can use. So we need to think about what is each agent maximizing for. Let's forget, we're going to want to forget about the names when we kind of genericize this, but let's forget about the names. Let's forget about Alice and Bob. Let's just look at if we have 2 agents who are going to want to make a choice at any decision junction, what are they ultimately trying to do at that decision? Well, the agent is going to want to make the choice that maximizes their score. They're going to want to maximize the difference between kind of this decision and whatever other results can come in terms of score from the rest of the array. And they want to kind of distance themselves given how the game unfolds below them. And so the parameters to our subproblem, as we saw, were the left and the right of the subarray. We're considering a subarray from the left and the right. And we want to maximize our distance from the other kind of player's result or kind of the score result. So we always come ahead net across all of the subproblems. So let's think about the base case. So if we have a single item, meaning this left pointer equals the right pointer, we just have a single item. What is the agent going to do? They're just going to take the item. They're just going to take the item at pile's left pointer or pile's right pointer, and that's going to be the best way that they can distance themselves from the other player's performance and kind of just get ahead. This is the best way to get ahead at this point if there's a single item. So that's a base case. And so I want you to think of this as the best score by a player starting on the subarray left to right. That's what you should see when you see this function. And that's the original problem. What is the best score by a player starting on this global subarray? Who's starting? Alice. Alice is starting, but forget about the names. It's just what can an agent do best starting with this subarray? So I just want to really frame that because it's important so you kind of see how this all kind of loops together. So let's imagine that there's more than one item. Let's imagine we have two items. Let's imagine we have two items here. We can either choose this item or we can choose this item, right? So for example, say we have this 2 and this 1. This agent can either choose the left item or they can choose the right item. And so they're going to want to compare how net ahead does this decision get me versus what the other agent achieves with the rest of the game. So if I choose the 2, the other agent who goes next, the best they are going to do is 1 coming back. That's kind of the base case here. They're going to come back with a score of 1. If I choose the 1, the agent's going to come back with a score of 2. They just take the other item. And so, I want to maximize my distance from the other agent's performance. So, this is going to put me down by 1. This is going to put me up by 1. So I'm going to, if it's just a 2 and a 1, the game is going to end with me up 1. If I choose the 1 and then leave the other agent the 2, I'm going to be down 1. So I want to choose the maximum that gets me net ahead of the other agent. So I'm going to want to take the left. I'm going to want to choose, this is going to come out to a 1 plus 1. This is going to come out to a minus 1 as quantity. I'm going to want to choose the left. So this is the direction I would have wanted to go given how the agents performed in the rest of the work. And so this bakes in all the optimality. This recursion, which bases out here, this is the point of knowledge, our base case. This recursion bakes in all the decisions of the back and forth and says whatever the agent comes back with their best score, hey, other agent, come back with your best score. I want to distance myself as much as possible from that. And kind of take the maximum of those. So the best score I can get is the best I could have distanced myself in this kind of sub call, right? And so that's kind of the best way to see this. We're baking many layers of recursion in and kind of finding what is the best this agent can do doing on the left and the right. So the global agent, Alice, operates from 0 to n minus 1, right? Operates on the global subarray. And if this score is greater than 0, it means that Alice is going to come away with the win because on this global, kind of game, Alice would have came net ahead versus the other agent. How would this play out? So this is very generic, and this is kind of the generic take we have on it. I want to make this more concrete. So let's look through a concrete example and walk through it. So let's imagine we start out with this array, this 3, 2, 1, and 9. So Alice is going to have the global subproblem 0, 3, 0, 3, the whole array. And then Alice is going to want to say, what is the maximum across kind of the differentials? What is the maximum across the differentials? If I take the 3 and then I see how best the other agent can do with the rest of the items, 1 to 3. If I take the 9, what is the best the other agent can do with kind of the 0 to 2? And so let's look at the 1 to 3 subtree. And if we just look at this example, what would Alice do? it's clear that Alice would take this 9. And, Alice wouldn't go down this subtree. But let's imagine Alice did go down this subtree. Then, if we look at this subtree, Bob is then going to do the exact kind of algorithm and kind of maximize the score. But to, kind of keep things brief, I just say Bob takes the 9. Bob would have taken the 9 here. He's left with the 9. Perfect. So now the game is down to 2, 1, right? Or yeah, this 2 and this 1, the subproblem 1 to 2. And so before I finish this subtree, let's go this subtree. So let's imagine Alice takes the 9. We're going to be left with 3, 2, 1 here. And then we want to see what's the best score the other agent gets rolling their dice on the 0 to 2. So now Bob is going to do what? In 3, 2, 1, the best he can do is take the 3. This is just, I'm not actually drawing out, the actual work, but we just know Bob will take the 3. I'm just, detailing out Alice's behavior here. So we know Bob's going to take the 3 here. And, we know we're going to be left with this 1 to this 2, right? And so this is the subproblem we were facing over there. It's the same overlapping subproblem. And again, this is why we're going to cache kind of our subproblems. So if I have this 2 and this 1, Alice can either take the 2, and then Bob is going to take the 1. This is the base case. Or Alice can take the 1, and then Bob is going to be left with the 2. We have a -1 and a 1. What is Alice going to do? Alice is going to take the 2 because it maximizes Alice's kind of score and pushing away from Bob in terms of score. And so Alice is going to choose that choice. And so in this, max diff 1, 2 subproblem, Alice chooses that. The best Alice can come out with is a, differential of 1. And then Bob asks himself, should I take this 3 or this 1? We said, Bob is of course going to take this 3, but, why is he doing that specifically? Well, if he takes the 3, we're going to be left with the 2, 1 subproblem. If he takes the 3, we're going to be left with the 2, 1 subproblem, or the 1, 2 subproblem, which Alice is going to come back with an answer of 1. And so 2 would be kind of the result of that. Bob could get net ahead. If he chooses this 3, Bob will finish the game with 4. So 3 chooses this, Alice is going to choose the 2, and then Bob would choose the 1. And so this is just, this is an odd number of piles. This is not how the global game would play out, but this is just a subgame. Let's imagine that Bob took the 1. So if Bob takes the 1, then we have this 3-2 game going on. Alice is going to take the 3, and then, Bob is going to take this 2, and then Bob will end up with 3, Alice will end up with 3, and it's basically going to be a tie. So let me adjust this. And so the Bob would be able to distance himself by 1 here, or he can distance himself by 2. So he's going to choose to distance himself by 2 here by choosing the 3. And then if Bob takes the 3, then he's going to return, if Bob is the agent going first and he has this 0 to 2 to work with, how much of a differential can he achieve against this subarray? It would be 2, because he would choose this 3, and then Alice would choose this 2, and then he would choose this 1. It'd be 4 to 2. And then, 2 is the differential he achieves as himself, as Bob. And so now this is where we tie it all together. And this is why a concrete example can help. Now Bob's going to return for the 0-2 subcall and say, okay, the differential I achieved was 2. Back here, Alice did not know whether choosing the 3 or the 9 was a better choice, right? Alice said, what would an agent do if they did their best with this subarray? What would an agent do if they did their best with this subarray? And I trying my best, and Bob trying his best. So now Bob's going to return 2. So if we choose the 9, the best the other agent can do if we're competing against them, how would that competition turn out? There's going to be a differential of 2. How would the competition turn out if we chose a 3 and we left this subarray, right? It would come out that the other agent would beat us by 8. Why would that be the case? Well, if we choose the 3, we're going to have this 2, 1, 9. What is Bob going to do? He's going to choose 9, and then Alice is going to choose 2, and then Bob's going to choose the 1. So Bob gets 10, Alice gets 2, and then, the other agent, the agent that starts with that subarray, is going to get 8. And so this is a lot to take in. So you might want to kind of rewatch segments, but okay, finally, Alice can reap 3, and then how could the other agent starting have done in the rest of the subarray? They would reap 8, or Alice can reap the 9, and then how would the other agent have done 2? What is the best choice? Alice wants to make the choice that distances herself as much as possible in this call. And so it's going to be competition between 7 and a competition between -5. This is a loss. This is a loss, and this is a win for Alice. And so, hopefully all of these numbers have worked out are correct. The key thing is to take away that the core subproblem is if an agent were to start with this subarray, what is the kind of best kind of differential they would yield? And so the global question is, if Alice starts with everything, Alice is the starting agent, what is the differential, right? And so, it's -5 versus 7, and we see Alice can pull away with a +7 here, a +7 win if Alice chooses the 9. And so Alice does do that. And what would that game end up as? Alice would take 9. Bob would take 3. Alice would take 2. Bob would take 1. And then it would be 4-11. And then the differential would be 7. So this is a concrete example of kind of how all of that pans out. So, let's forget names for a moment. Let's forget about names. Every player chooses a pile that gets them the most net ahead, given what the other does. And we quantify that difference against the remaining result and so on. So let's look at an implementation. I think we can hop into the implementation now. So we're going to have the piles passed to us. We're going to just extract n here. And we're going to keep a mapping. We're going to keep a key. And I have this get key function. So for a subproblem with this left and right pointer, so again, this max diff left and right, we're going to cache the subproblem because as we saw in the concrete example, the max diff, we had overlaps. An agent starting with the subarray 1, 2, what is kind of the best they do in terms of differential? And so we want to find out if an agent starts with left at 0, right at n-1, piles, and we pass in the piles in the memoization table. If the max diff can be greater than 0, this agent starting with the global subarray is the winner. What does that mean? It means Alice is the winner. Now we're bringing names back into the picture, and this is the original question. Is Alice going to win the game? And so we have those passed here. What's the base case? If the left and pointer are equivalent, we just return the item. It's a single item, right? And then here, if we actually need to do processing, we grab the key, given the left and the right kind of values, and then we check, does the memoization table have that subproblem already solved? If that's the case, we get it from the memoization table. Here it's just a hash table, it's just a mapping. And this is going to be an O of 1 kind of reach in and grab, and we just return it. If we have not found that, it's very simple. We just implement the top-down recursion we specified here. The hardest part is getting the recurrence. And so we're going to get the best differential on the left, which is I grab the left item, and then best differential on the right, I grab the right item. And then what does the subproblem become? I took the left item, so I close in the left pointer. If I took the right item, I close in the right pointer. Left stays the same here, right stays the same. If I took the left item, right stays the same. Pass on the piles and the memo table. And then finally, the best differential, the best between these that distance me the most at this decision junction, I'm going to want to take. So between these, what's the best kind of diff? And then I set that in the memoization table and return that best difference. And then at the global subcall, we're going to see if Alice could have won the game given optimal agent behavior at every single point. And so how many subproblems are there? Well, if we kind of look at the combinatorics of, what are the parameters? It's the left and right of subarrays, right? And remember, we've counted subarrays before. We've done problems with subarray sum, and it's going to be a quadratic amount of subarrays, right? And so let's imagine, how many subarrays could we choose? If we had a left pointer, ... there'd be kind of n-1 or so other subarrays, a linear amount of other subarrays. What if left is here? A linear amount. What if left is here? A linear amount, and so on. These left and right boundaries, this left can be in how many points? It can be in n places, n places. And then the right can be in, a linear amount for the others. It creates a triangle of work here, and that's going to turn out to be quadratic. And we see this in many other problems. And then in terms of space, we're also going to have, kind of a quadratic amount of subproblems. I'm max filling the table. But then the question is, but this is recursion, right? Well, we're memoizing the recursion. So at maximum, we're going to solve these n-squared subproblems and then have constant time access afterwards. So a good video to review would be the video on memoization. We're not going to solve more than n squared subproblems. We're not going to redo kind of recursion trees. We're going to prune it and have O of 1 access, and so on and so on. So we went through a lot in this problem. We went through the dynamic programming solution. We kind of looked at, game theory-esque problem, and we drew out a recurrence, and we saw the subproblem. We actually saw this from the first slide. We saw that a subproblem could exist, and we wanted to optimize for optimal agent play at every single step. And so we went from there. I really like starting out with recursive brute forces. I really like how that kind of sets us and gives us a way to kind of see the dynamic programming later. So yeah, a recursive brute force is a really good place to start and kind of really get your feet in the problem. And so we also looked at kind of optimal play from each player, and kind of general thoughts about the problem, observations. And so, this is the problem stone game. You're going to see many kind of variants of this. And, stone game is just kind of a name here. Really, this is a game theory problem of having two agents acting and choosing, from either side of this. So this is a problem called stone game. If you enjoyed that video, you can get a lot more content just like this on interviewpen.com. We publish 2 to 4 videos a week. Really, it's just an arbitrary number. It's whenever I can sit down and do a video because these videos take a whole day to do. And we're always online to answer any questions you may have. Join our Discord, join our newsletter, The Blueprint, where you can get more weekly data structure and algorithm and system design kind of topics. And subscribe and like this video if you actually like this video and it helped you. And also tell a friend that we exist. That's all.